Okay, I think let's recall back what we learned last class. So we learned about induction, electromagnetic induction, something to do with generator. We learned about magnetic flux. Flux is the B dot A, magnetic field strength, normal to the surface area and the area. If the A is a little tilted, you see this angle, then you have to find the vertical component, B cos theta. Okay. So sometimes there is one year, I think they keep the B like this, the B, but they keep this angle. They keep this angle. Then they're asking for the flux. Okay. Asking for the flux up to that. So here, the area. So for this case, you need to get the vertical component, but this is going to be B cos theta or sin theta. This will be sin theta. Okay. So then the B dot A will be sin theta. The angle between the magnetic field and the surface area is given. Okay. The one most of the time they give is the magnetic field with a normal line. This angle is given. You see this diagram? If the theta is between the magnetic field and the vertical line, then you use cos. Most of the time cos. Okay. So the unit is Weber, and magnetic flux linkage is NBA cos theta multiplied by n. Then we did this question. Then we talk about how electromotive force is produced. Electromotive force is produced when there is a change in magnetic flux linkage. Magnetic flux linkage, you change, you got EMF. If you have a closed loop, it's going to lead to a current flow. Okay, we talk about Faraday's law. Okay, what is Faraday's law say? The induced electromotive force in a closed loop is directly proportional to the rate of changes of magnetic flux linkage. You have said linkage, magnetic flux linkage through the loop. Okay. Yeah. Then we talk about Lenz's law. Lenz's law state that the direction of the induced electromotive force, is always such as to oppose the change producing. This is a little tricky one that they will try to deal with. Okay. So we go back to the slide. Okay, so that day we tried out the part A. Okay, part A. We're still going to do part A. I want to ask extra question about part A. Okay, part A, we calculated what? What we calculated part A? We calculated what is the average induced EMF. Right. So we calculate what is the average induced EMF. And we use the, of course, the EMF equals to d psi over dt, and we calculate the answer. Okay. Then, but now my question is, when this coil moved out from the magnetic field, it was displaced left, right? Did they say it is left? It's jerked to the left. It jerked to the left. Okay. So it jerked to the left. So now tell me, when this coil is jerked to the left, the current will flow clockwise or anti-clockwise? Use your Lenz's law. Tell me. And this frame was moved here. The frame is now here. The frame was moved to the left, to a region where no magnetic field at all. The current will flow clockwise. The current will flow clockwise or anti-clockwise.
Be clockwise.
So it's going to be clockwise. Okay, as we see clockwise. So clockwise means you are saying the current should flow this way, going down here and going up here. So why you say clockwise? Because when you move the coil outward, what happened to the flux? Flux decreasing or rising? When you move the coil outwards, the flux is decreasing, it's going down. So according to Lenz's law, the current, the EMF or the current opposes the change. Okay, the change is the flux is dropping. So you need to rise the flux back. So therefore, the current must create a magnetic field the same direction to the original magnetic field, because you need to rise the flux back. Flux is dropping, so but the original magnetic field is into the page. So the current also going to produce the magnetic field into the page. So use right hand grip rule. Put your finger along this wire. Right hand grip, your thumb must point into the page. So yeah, I think your current should flow clockwise. Very good. Should be clockwise. So those who got clockwise, good. Correct idea. Okay, now think about B. Okay, B. Okay, B. Faraday's law, Lenz's law. A rectangular coil A is moved back to the original position. The coil has been moved back to here again. Okay, its magnetic flux density decreased from 2.5 to 0 in 0.8 seconds. What happened? They moved back the coil here. Okay, now they already moved back the coil. They never move the coil anymore. Now the coil is at the center of the magnetic field strength. Now they adjust the magnetic field strength. The magnetic field strength from 2.5, it dropped to 0 in 0.8 seconds. So B is changing. B is changing. So first question, calculate the average induced EMF in the coil. Okay, so find the EMF. So according to Faraday's law, what is EMF? EMF is rate of flow of negative rate of flow of magnetic flux linkage. Rate of flow of magnetic flux linkage. This is the original way of writing. Original way of writing. So minus, you put final flux minus the initial flux over the time. Get the answer for the EMF. Okay. So now, is there flux changing? Flux should change, right? Because the magnetic flux linkage, the flux is made of what? Made of three component what? B dot A and N. B A N. If any one of them changing, the flux will change. Okay. So in this case, I think the B is changing. Magnetic field from 2.5 drop to 0. So because there is a change in B, I mean there is a change in flux. Flux is dropping or rising. Original flux was 2.5, very high magnetic field, then later becomes 0. So flux is dropping. Flux is dropping. Final flux is smaller than the initial flux. Okay, so calculate the EMF, please. Final flux is 0. Okay. So BAN of final minus BAN of initial. Okay, so if I go back to the answer, this is the working. So negative d psi over dt. Yeah, the B is changing. Final B minus initial B. Okay. And final B is 0. Initial B is 2.5. And A, you can put it out. Negative. Final minus initial R. You get 1.125 volt. You get 1.125 volt. Okay. So I hope everyone get 1.15 volt. Okay, because the B changing. B changing, flux changing. Okay, any problem here? Okay, so we go back. Okay, next. 2. Indicate and explain the direction of the induced current in the coil. Indicate and explain the direction of the induced current in the coil. Okay. Can you tell me where's the direction of the current now for the part B? Use your Lenz's law. Use Lenz's law to calculate the direction of the current in this coil. Current will flow clockwise or current will flow anti-clockwise. First, the magnetic field is decreasing. So flux dropping or flux rising? So we found that flux is decreasing. Flux is decreasing. Magnetic field 2.5 becomes 0.0. flux is decreasing. So the current must try to rise the flux. You don't like the change according to Lenz's law. So the current should flow such a way that the flux is raised. So you must create a field the same direction as the original field. So again, the thumb point into the page, your current is found to be clockwise direction. Clockwise direction. Okay, yeah, B. So external magnetic field directed to the plane of the coil. By Lenz's law, the induced current must flow in the clockwise direction, producing a magnetic flux directed into the plane and directed into the plane of the coil, restoring the decreasing magnetic field. So it opposes the change. Okay. So I hope you understand the wording. The external magnetic field B is directed into the plane of the coil. Okay. By Lenz's law, the induced current also must produces a current must flow clockwise so that it produces a magnetic flux directed into the plane, or the magnetic field directed into the plane. This magnetic flux can replace with magnetic field also directed into the plane to restore the decrease in the magnetic field. Lenz's law opposes the direction of the current is always opposed the movement which produces it. Okay, so that's the B. Okay, now look at C. One minute for you. The magnetic flux density is increased to 4.5 Tesla. Okay, now this is not anymore 2.5. They put it 4.5 now. 4.5. Find the induced EMF in the coil if it rotated 90 degrees in 0.3 seconds. So the magnetic field now is 4.5, not anymore 2.5. What is the induced EMF? When the coil is turned, rotated clockwise. Sorry, they never said the direction. They said rotated through 90 degrees. So this is the ABH. Let's say, okay, this is your ABH. AB was rotated. They never tell which direction, but let's say we go this direction. Then what we see, we're going to see the frame like this, AB at the side, after rotate 90 degrees. Okay, after rotate 90 degrees. So tell me, this coil rotate 90 degrees, flux drop or rise? Flux B dot A drop or rise? B dot A drops what? Finally, the AB will be only like this side. The area is we consider as 0. No area it covers. So the final flux is said to be, final flux is, of course, is 0. The initial flux, of course, B dot A dot N, this value, but B now is 4.5. And this rotation happens in 0.3 seconds. So the time is 0.3 seconds. So find the EMF as usual, negative d psi over dt. So negative final flux minus the initial flux over the time. Final flux is 0. Okay, so we go back to the working. So this should be a working. So the average EMF is negative d psi over dt. Final flux minus initial flux over time. Final flux density is the initial flux density. Okay. Final flux NBA cos 90 what? 90 degrees is actually 0. It's actually 0. Cos 90. It didn't put cos 90 also in final line. It's going to be 0 and no area. So this one originally the maximum flux NBA only NBA. I think you don't need to put cos 0 cos 90. NBA 0. Yeah, 0. It's 1.62 Weber. So final flux minus initial flux over the time taken 0.3 minus 5.4 volts should be generated in the coil at the edge of the frame. Okay, 5.4 volt. Okay, any question from this slide? Okay, no question. Okay, so put it in mind. ABC tells you 3 ways you can generate EMF and current. You move the coil outward, or you don't move the coil, you change the magnetic field strength, also you get EMF inside. Like what happened in transformer. Transformer, the coil does not move. The magnetic field is the one changing. The part B style is adapted by transformer. Part C, the coil was rotated in a generator. In a generator, coil is rotating. The coil experience changes in magnetic flux. So the age of coil induced EMF, because it's a closed loop, current is start to flow. Okay, so you get electricity. Okay, so the C is adapted by generator. But whatever it is, you want to get EMF, you must change magnetic flux linkage. Okay, magnetic flux linkage need to be changed. Okay, yes. Okay, class, one example and solution. Read the question and try to understand the solution. Is there any mistakes in the solution? 1 minute for you. Okay. A solenoid of consists of 600 circular coils of wire. The radius of 5 centimeter. It's placed in a uniform magnetic field with angle of 30 degrees. So this is the coil. The coil is got 600 turns. 600 turns. That's your N. And the coil axis was this way. I believe if you know the coil, the magnetic field direction should be this way, right? This is your B direction actually. This is your B direction. Oh, sorry, not the B. B is, sorry, the coil does not have current. We don't have B. The B was applied here horizontally. I thought the coil got current now. The coil does not have current. You're going to generate current. Sorry. So B is horizontal, N is 600, and the coil plane was 30 degrees. The surface 30 degrees up. Okay. The surface area, the surface area is like the plane is 30 degrees upwards compared to the magnetic field. Okay, now they said the field decreases. This is something new. The field decreases at a rate of 0.4 Tesla per second. The field has been decreasing in order by 0.4 Tesla per second. What is the magnitude of the resultant induced EMF in the coil? So the surface area is like this. The area is here. The coil is horizontal and it makes 30 degrees. First, of course, the formula you must use is NBA cos theta is the flux. NBA cos theta should be the flux formula. N is 600, B is the field strength, and A cos theta. Okay. So you want magnetic field strength, the EMF, the EMF is the negative of the rate of changes of magnetic flux. Okay, rate of changes of magnetic flux. So negative NBA cos theta. You can straight away go here. NBA cos theta, cos 30. But here you must know it's NBA cos 30. NBA cos 30. So NBA cos 30. Over time give you the EMF. But B over T, you know already. B over T. B over T is how much? 0.4 Tesla per second. So just B over T replace as 0.4. Tesla per second. And A cos 30 we apply here. The area is pi r squared. Pi r is r, the 5 centimeter change to radius, so 2.5. In meter is 0.0025, right? Yeah, sorry, the 0.25 in meter. So put that value, so you get the area of 0.0025. So you get 1.63 volt. Okay, this is the voltage generated in the coil. Okay, in the coil. So when the magnetic field is changing. Okay. So B over T got value. So B over T, kept it, just put it together, you can replace as 0.4 Tesla per second. So this is the working on how to find the voltage. Okay, any questions from this slide?
So where's the negative go?
Okay, the negative is there. Oh, you can put the negative 1.6. Yeah, I should have negative, right? BA. The field decreases, what? The field decreases, right? The rate of field decreases is 0.4 now. That means the B over T itself is a negative value.
Oh, all right.
B over T, because it decreases in order rate. So it's negative 0.4 rate. Okay. Yeah. Okay. So next question. Okay. Understanding more about the concept. We almost done the topic. These are the two laws. Another one part is waiting. Okay. So very fast. Let's go through this. 1 minute for you. One magnet here, another magnet here. The two solenoid connect together by long copper wires. The two magnet P and Q are suspended. Okay, the magnet P is set to oscillate, or the P is oscillating up and down. Okay, then they say, state and explain the polarity of the solenoid A, B, C, and D. When bar magnet P moves towards and away from A. First moving towards, when the P is moving towards, what is the polarity of A and D will be? A, B, C, D. D1. Okay, first A lah, first A. When the magnet go down, north pole, A will be what pole? A should oppose this movement, right? North pole means the edge going to induce what pole? Current will start to flow in such a way that the top going to be north pole. Okay, so A going to be a north pole because you need to repel. Okay, because the magnet is going down, the coil makes a current flow because you want to oppose this movement. So it creates north pole up here, north going to repel, so you can slow down the magnet movement. So A is north pole for sure. So because this is north pole, the down here going to be a south pole, of course. So use your right hand grip rule. Use your right hand grip rule. Your thumb should point upwards. Your thumb should point upwards. Your finger should be this way. Okay. So your thumb, sorry, your finger is here. This is your finger, right? Is here. So I think you have a current flow this direction. If you view from the top, the current should flow anti-clockwise direction, right? Anti-clockwise direction. So current flow this way and come to this coil. You tell me, D or C? D is what pole? Use your right hand grip rule again. Okay, your fingers all should be pointing down here. Your thumb will be this way, right? Your thumb will be this way. Thumb will be this way. So your D going to be, of course, north pole, and this is going to be the south pole. Therefore, yeah. So north pole, A is north pole, P is south pole, C is north pole, D is north pole, C is south pole. Okay, describe the motion of the bar magnet Q. When this oscillates, when this first magnet oscillates, how the Q magnet going to move? Okay, how it's going to move? So when this oscillates, the D pole going to be north and south alternatively, because when go down, A going to be north, D going to be north. When this magnet goes up, A going to be south, D going to be south. So north, this magnet going to be repelled. When the D is south, the magnet will be attracted. So what happened? Describe the motion. The magnet going to, of course, is going to oscillate with the same frequency as the original magnet. If this frequency is 50 Hertz, this magnet also going to oscillate with 50 Hertz. So the oscillation will be, there will be an oscillation with the same frequency as the original magnet. So that sounds. Okay, so the A is north pole, B is south pole, the one we discussed. And move away, then the pole is going to change. Last part, bar magnet will be set into a horizontal oscillation motion. Okay, and frequency going to be the same as the frequency of the spring oscillation. Any questions from here? Okay, let's move forward there. Okay, so now comes in Fleming right-hand rule. Okay, don't mix up left-hand and right-hand rule. Okay, Fleming right-hand rule you only can be used for generator. Fleming left-hand used for motor. Okay, motor. For example, how do you know it's a motor or generator? You check what is produced. Okay, for example, for a motor, for the case of motor, what I told you the early of the lesson, what plus what gives you what? Motor. You apply current, the inside got magnetic field strength, you get a force. So if you see a device with the battery, the circuit as a battery, then it's definitely a motor. If there is a battery or a power source, it's a motor. Okay, so motor use Fleming left-hand rule. Okay, for the case of generator, what plus what gives you what? Of course, generator gives you the EMF. Okay, or another word gives you I. Okay, I put I here better. I. You apply force, you push the coil. Inside got magnetic field, so you get current. This is generator. If you see a coil where movement happens, but there is no power supply. There is no power supply, no battery. No battery. You might have voltmeter, but no battery.
So you muted yourself.
Plus, how long muted?
2 to 3 minutes, I think.
Oh yes, yeah. You come to me. And you heard this explanation, I know.
Yes.
You heard this explanation.
Yes. Yes.
Okay. Hey class, so this one you totally okay. Hey class, so Fleming right-hand rule, Fleming right-hand rule. When to use Fleming right-hand rule? When it's a generator. Okay, just now I wrote generator. Generator you use, if it's a generator, use Fleming right-hand rule. Okay, how do you know it's a generator or motor? For example, this diagram, is it generator or motor? Generator, what plus what gives you what? What plus what gives you what? Generator.
Force plus.
Force plus V equal I.
Yes, good. So it's a generator. When you get a current, there is no battery in the circuit, then it's a generator. Okay, motor, of course, how do you know identify as a motor? If you have a battery. If you have a battery, then it's a motor. So this diagram is a generator motor. So this is a no battery. There is no battery. The bar is only moved to the right. So it's a generator. So if it's a generator, if they ask where's the direction of the current or direction of magnetic field, in this case, they're asking for the direction of current, let's say, you have used Fleming right-hand rule. Okay, Fleming right-hand rule, your thumb is motion, force, or this is your force. Thumb is force. Your magnet is, your index finger is your magnet, your B, and this is your current. You now look at this diagram. The bar is moving to the right, so the force is to the right. Okay, magnetic field is into the page. So which direction the current should flow? Use your Fleming right-hand rule now. F, B, I. F pointed to the right. F point your thumb to the right. Your magnetic field is into the page. Your index finger must be pointed into the page. Your middle finger, your current should pointed upwards here. The current in the bar, moving bar, the current should flow upwards. So therefore, it completes the circuit. Current will flow this way, in a what? In a anti-clockwise direction. Okay, any problem with my explanation? Any part you don't understand? So make sure when to use Fleming right-hand rule. When do you use Fleming right-hand rule? If it's a generator. How do you know it's a generator? No battery is there. Okay, movement create current. Then it's a generator. If you see a battery here, then it's going to be a motor. Okay, so this is a simulation of generator. Okay, now look at this. The EMF produced is rate of changes of flux, flux linkage. Because it's only a one bar, so it's only B dot A. B dot A over T, there is no number of turns here. So, okay, you see here, the area, here, what is the area? The area is the area it swipes. The area it swipes. Let me show you something. Okay, let's say you have a conductor. There's a length of L. This is called a magnetic field. Okay. It has its own circuit. Okay, you have put a ammeter, its own circuit. This bar you move forward. Okay, move forward. Okay, now what happened? This bar experienced changes in magnetic flux. So what is the EMF induced by this bar? Is rate of changes of magnetic flux. Rate of changes of magnetic flux. Okay, negative. It's B dot A. N is 0 because only one conductor. B dot A over T. Okay, but A, what is the area here? Let's say this conductor move forward with the speed of V. Okay, with the speed of V, and it's at L. Okay, after it travel a certain speed, okay, after it travel a certain speed, let's say finally it's here, the area it swipe, this is the area it swipes. Okay, this is the area it swipe in a certain time period. What we do here, negative b dot, the area, right? The area we can represent in terms of L and B. The area swipe, how you link to L and B? Area is what? Area is length times this horizontal distance. What? This horizontal distance. And this horizontal distance in terms of V should be V times T, right? Plus, can you listen to me?
Yes.
And okay. So the area will be L times this distance. Let's say the horizontal distance, I put a Y. How the Y and B related? Speed equals to distance over time. What? Distance is the horizontal distance Y. So the Y is actually V times T. So V times T is the horizontal distance. So L times V times T, L times V times T will be the area. Okay, the area is what? So here the area we put LVT over T, cancel the T. So the EMF induced is actually BLV. Okay. Cambridge normally they ignore the negative, so it's a BLV. Okay. So the EMF going to generate in a conductor, it depends to how strong is the magnetic field, how long is the conductor, how fast you move it, how fast you move forward. Okay. So that's what described here. Okay. Okay, so the BL, so A is actually LVT over T, the dt is T lah. Dt cancel, so you get BLV. This is your EMF induced in this coil, in this conductor. Okay, EMF increases with increasing the B, L, and B. More faster you move the conductor, more greater EMF will be induced. Okay. Okay. So this is another one question. Okay, before I go to this question, okay, I want to teach you another one. Okay. Go back to the slide again. Okay, class. You see, EMF is negative d psi over dt. Okay, so EMF is negative BAN over time. If I want to put it in the time. Okay, so in exam, they will give you the flux graph. They will give you the flux graph. They ask you to plot the EMF graph. Okay, so you have to know this flux graph. Okay, so let's say the flux graph is a straight line like this. Okay, how's the EMF graph going to look like from this relation? So again, the best thing is visualize the EMF and the flux like again like acceleration and velocity. Acceleration is dv over dt, right? A is dv over dt. EMF is negative d psi over dt. The velocity, the flux is analog to the velocity. The flux is analog to the velocity. And the EMF is analog to the A, but only negative. That is the negative. So you need to do reflective. Okay, now, if the flux is a straight line, you imagine this as a velocity graph. The EMF, assume like the acceleration graph first. The velocity, if flux is a straight line, how's the EMF graph going to look like? Like a velocity. So velocity is going like this. Acceleration going to be a constant line, correct? The acceleration is going to be constant one. Okay, so the graph will be a flat line. Okay, but that's the acceleration graph lah. To get EMF, you must make it negative. You must reflect the x-axis. Therefore, it won't be here. You have to reflect it at x-axis. The graph is going to be like this. So conclusion: when the flux is a straight line with a positive gradient, the EMF is going to be a flat line with a negative value. Okay, so what do you do? Imagine the flux as a velocity graph, get the acceleration, you reflect it, you get the EMF graph. Now, let me show you another flux graph. Flux graph is going sine. The sine. How the EMF graph should looks like? Anyone? Is it going to be sine? Is it going to be cos? Is it going to be negative cos? Is it going to be negative sine? What shape going to take? Because EMF is negative d psi over dt. Flux is sine. So imagine your velocity is like sine. How the acceleration graph looks like? The EMF, we take it like acceleration before we reflect it. Okay, sine, velocity is sine. Acceleration should be what graph? What trigger? Because velocity is what? Sorry, acceleration is what? dv dt, what? Right? So the velocity is sine. You need to differentiate, right? dv dt is differentiation. So sine you differentiate, you got cos, right? Cos. The constant, yeah. Sine you differentiate, you get cos. But now you reflect it at x-axis, it's going to be negative cos. Okay, the graph should be negative cos for EMF. Okay, so you got the idea. So they give a flux graph, you must know how to draw the EMF. Just imagine the flux as your velocity, draw the acceleration graph, reflect it at x-axis, that's your EMF graph. Okay? Okay, let me give you more. Now, the flux graph is let me. It's like this. Okay, this is 1 second. This is 2 seconds. This is 3 seconds. Okay, plus 1, 2, 3. Okay, how's the EMF graph look like? Please catch for me. EMF is negative d psi over dt. Okay, draw the first one, second one, and the third one, part by part. Draw the first one first. The flux, imagine as your velocity. The EMF, imagine like your acceleration. So draw the acceleration graph first for you. How the graph going to look like? Okay. So one, like velocity is like with a constant gradient. So the acceleration will be what? Positive gradient, right? Positive gradient, flat line. Right? Velocity is increasing in a constant gradient, so acceleration is constant. 2, velocity is constant. A will be what? 0. 0. And 3, velocity is with a negative gradient, so acceleration going to be negative. But this is your acceleration. But you want EMF, what? So EMF, what do you do? So it's just reflection of x-axis. So this one going to be going down. So therefore, it's going to be down here. Then the 0 still will be 0. Okay, 0 here. And the negative, the third one will be reflected up. So it's going to be up. Okay. So this is going to be your EMF. Okay, can understand? Can okay, any questions from here? Okay, I believe you can cope up. Okay, now the question is, sometimes instead of flux, they give current graph. Current graph means maybe you have a solenoid, which has a current flow, which produces the magnetic field now, produces magnetic field. And the current here changing, the magnetic field here changing. Maybe you have a coil here, you might have a coil here, coil generate EMF. Okay, so they keep the current graph of this coil. Remember, the flux is actually made of what? B dot A dot N. Okay, so the I is actually affecting which property? N, A, or B? The I. The I in the solenoid affects which property? The magnetic field strength. So inside the B, there is I. Current controls the B. Okay. So if a current graph given a sine graph, let's say sine graph, and the question in exam, they will ask for let's say EMF induced. They give a current graph. So we are very used to it with the flux. Then we can get the EMF. But this is current. First, you need to get the flux graph first. Then you find the EMF. Okay? Because the flux is the one linked to the EMF. If the current is sine means flux going to be what? Sine, cos, negative sine, negative cos. What do you think? Current is sine. The current changing in the solenoid is sine. It means I is sine. If I is sine, B going to be what? Sine. B also sine what? If I is sine, B also going to change in terms of sine. Because the B and I is directly proportional actually. We don't know this story, but greater the I, greater the B. So if I is sine, B is sine. So if B is sine, flux going to be sine or what? Still going to be sine, right? The conclusion is if they give I graph sine, the flux also going to be sine. So I graph is actually same like flux graph shape is sine. Okay, that's the point I'm trying to tell you live. They give I graph, flux graph is the same shape. Sometimes they give magnetic field strength graph, B graph, B versus time, let's say sine. If B is sine, flux also going to be sine, right? Because flux is B dot A dot N1. If B is sine, flux also going to be sine. So conclusion what I'm trying to say is I, B, and flux always will have the same shape. Yeah. Pattern. Same shape. The pattern is the same pattern. If I is sine, B will be sine, flux will be sine. EMF, you need to differentiate, and what we did just now. Okay. Okay, I hope you understand. Okay, let's go to the word file. Okay, can you draw for me? This is the last part of this today's class one. Can you draw for me how these two graph looks like? This is IP, IP. Current. This is the current graph. How the flux graph looks like? How the EMF graph looks like? Can you sketch the graph here? The I graph is what shape? Fine. So EMF is negative BAN over T. Flux is B dot A dot N. Okay. Inside I, we have inside B we have I. Okay, inside B you have I. B is proportional to I. Right. Yeah. Okay. So anyone? So what's the flux graph going to be? Same as I. So it's going to be a sine graph too. Sine graph with the same period. Period at t. So here also t. I B flux, same graph. Same graph. Okay. How EMF going to look like? Sine, cos, negative sine, negative cos. Okay. So flux, you imagine as your velocity, you get your acceleration graph. Yeah, sine, you differentiate sine, you get cos, but it's going to be negative cos, but reflection of x-axis. So it's going to be negative cos. So negative cos, like this line, negative cos. This should be a period. Then this pattern is continuous. Okay, so this is how you should draw the graphs. Okay. Okay, class. So any problem? So any IB flux graph provided, you should be able to find the EMF graph. Okay, from this relation. So maybe you can very fast. Can you get this answer? Now this I is like this. How B and E graph going to look like? Magnetic field strength and the EMF graph going to look like? I is negative. I is cos. So B is what? So B also going to be cos. Okay. E is what? B is like your flux. B you can imagine like a flux. Flux, if I is cos, B will be cos. Flux also going to be a cos graph. So E will be what? So differentiate the flux, imagine like your velocity. So you get the acceleration. Cos you differentiate, you get what? Negative sign. So reflection of x-axis become what? Become sine. So your E should be a sine graph. It should be a sine graph. Okay, like this. Okay, and so on. You repeat the pattern. So this one period. So this will be another period. The pattern will be repeated again. Hey guys, any question? That's all for today. Okay, so I stop here if you don't have questions. So you learn about drawing graph today. We almost done another 1 hour. We finish up this topic. Okay. So if no questions, see you tomorrow. Okay, thanks.
Thank you, sir.
Thanks.